hadn't alt-tabbed, so it's still on the end stream button.
Oh, no.
So space happens every time. Like if I give a 5 minutes of introduction and then here's the announcements, whatever, space bar. Oh. So anyway, hello again. Sorry about that. By the way, I did post your first homework. I meant to email. I will send an email to note that. I think it's due in a week from today. So you'll have that. It's essentially on kind of the basics of units, mass balance, chemistry stuff, and kind of reactions, mass rate orders, sort of dealing with that kind of thing. I do have a rather challenging chemical equilibrium problem on that. Again, these are going to be graded for completion, so give it your best shot. We'll go through it, and when you find that one, maybe next time I'll kind of give you a little suggestion on how to think about it before that's due. Okay, so anyway, we were talking about sedimentation. We're going to finish up our discussion on sedimentation itself, and then start looking into how to advance from there and enhance the sedimentation with what we call coagulation and flocculation. And so then that's really where we're going to start seeing for the first time our mass balances in practice. Okay, but for this problem, I wanted to quickly go through my process for solving it, and hopefully that can give you a kind of some guidelines on how to think about this particular problem. I also have, let me just pull up a quick Excel sheet. Okay. All right, so first of all, we're given some text, and my advice to you is to always look at what you're given and draw it. So some problems might have a picture, but in this case, it just says we have a circular sedimentation basin. And so I would draw that, and since it's a sedimentation basin, it has to have some height. So this would be a cylinder, right? So this is going to be some form of a cylinder, and I'm sure that I did not draw that to scale because it's most likely going to be a lot wider than it is tall, right? So maybe something like this would be a little more appropriate. So you get the picture, though. We have some flow rate through it. That's given in million gallons per day, but we're also given some conversion factor. So I'll just go ahead and write the Q. That's 3 mgd, which is the same as 3 times that conversion factor they give us, which was 0.438 cubic meters per second. And so as I'm going through this, I'm just saying, oh, there's a piece of information. I'm going to write it down. If it's convenient, I'll go ahead and convert the units into something that I think I'll probably need, even before I even think about the problem. So I'm just sort of organizing the information. Then we're given, let's see, after that, it says after a storm occurs, upstream river carries 0.01 millimeter silt particles. And so it's giving us some information about the diameter of particles. It's definitely going to be different than the diameter of this basin, right? So we have some basin. It's going to have some dimensions. It's going to be a lot larger than 0.01 millimeters in terms of how big the clarifier is. So that's definitely a potential source of confusion if you're not thinking about the physical aspects of this. But so the diameter here, that's going to be 0.01 millimeters, and we can convert that and say that's going to be equal to 1 times 10 to the minus 5th meters. So the milli is essentially times 10 to the minus 3rd of a meter. And so if you already have 0.01, you multiply that by 10 to the minus 3, then you're going to be left with essentially 10 to the minus 5. Okay, so just writing that out, we're also given some information about the density of these particles. It's 2.2 grams per centimeter cubed. Okay. We're given a temperature, and using the temperature, we can get the dynamic viscosity up here. Get that out of the way. And so the dynamic viscosity and the density of the water, those will come into play when we calculate the sedimentation velocity of our particles. So I've got that written up here already. It is 3.5 meters deep. So the basin itself is 3.5 meters for that dimension. And it also gives us a diameter of 21 meters for the basin. Okay, so part A asks, what is the hydraulic retention time? And this is actually, you're given all this information and then you think, okay, part A, let's get into it. Let's put all these things together. Well, part A actually asks for very little of the information, right? So as you're thinking about it, make sure not to overthink, especially for these problems that are going to build to a final conclusion about the overall design. Sometimes it'll just start you off with, okay, now with all this information, what's that first simple part, right? So the hydraulic retention time, this is talking about what we call theta. That's V over Q. So we're going to need to know the Q and the volume then. So the volume is simply going to be the area of the basin times that height, which will be pi r squared. So pi, I'll go ahead and do a new line. So V will be pi times the radius squared, which is going to be the same as saying that diameter, 21 meters, divided by 2, and square that, times that 3.5 meter height. When we solve that, and I've done so in Excel already, we can say, oops. Okay. We can say that 3.5 times pi, 3.14, times 10.5, which is half of the diameter, right? That should be our radius. 10.5 times 2 is 21. So that's our radius squared. That should be then equal to 1,212. So 1212 cubic meters. Okay, so that's the kind of first task. Then we need the Q. Like I said, this is just 3 times that 0.438. So when we multiply that, that should give us, excuse me, it should have been 0.04. Sorry about that. So 0.0438, just missed that. We have that as well. If we just simply do that multiplication, that should give us 0.13 cubic meters per second. We could do more decimal places, and I probably have that in my Excel. We'll just leave it like that for now. Cubic meters per second. And then now we're in meters and seconds, which is good. That way everything can be compatible. So then we can say this is just simply 12 cubic meters per 0.13 cubic meters per second. This should give us an answer in seconds. So when we do that calculation, we get 9,226 seconds. But that doesn't mean a whole lot to me. 9,000 versus 12,000 seconds, and it's hard for me to conceptually grasp, what actually does that mean. And so I went ahead and converted it. You wouldn't have to necessarily, but if it's something like that and it's just asking for the time as the final answer, yeah, I'll definitely write down the seconds because I might need that later, but might as well convert that to minutes. 153 minutes, yeah, I could kind of do that in my head, but hours is even a little more tangible, I think. So I just went ahead and converted to hours. It's about 2.5, 2.6 if we round, hours. And that's why I had that unit for your Kahoot. I figured for the Kahoot, you could probably do that conversion if you had to. Give it a minute. Okay, so there's the answer to part A. Does that make sense? Any issues? Did some of you try to complicate it a little further beforehand? Yeah. Okay. So part B then is where we get into all the gory details of the V naught and the VS. So here's asking, will the clarifier remove all these particles? And essentially what's going on is we want to compare and say, is this settling velocity of those particular particles, that's VS, is that greater than or equal to what the reactor is designed to remove? That is the question. If that is true, then yes, it's going to remove everything, right? Because the particles settling at V naught are the ones that any slower, and they're not all going to be removed. Okay, so with that, we can tackle both of these. I'm going to go ahead and start with V naught first. And we have an equation for this, which is Q over the area of the basin. And if you ever, I think this is one, I can't remember if I'm telling you to memorize this one, but I'm memorizing it. So what I will say for myself is the way I will think about it is to double check myself right now. I'm like, oh, well, V needs to be in meters per second, right? So if I had this upside down, which I don't think I do, then it would not be meters per second, right? But it is currently cubic meters per second per square meters. So that leaves us with meters per second. So we're good. Just a little mental check for me, if not for you. Okay, so we have the Q. That was 0.13 cubic meters per second. And we basically have the AB. That was pi times r squared. So pi times 10.5 meters squared. And so when we do that one, did that here, and we're left with essentially 3.79 times 10 to the minus fourth. So right here. So that was just, again, the Q in meters per second, or cubic meters per second, divided by the area in square meters. So 3.79 times 10 to the minus fourth meters per second. And if you recall, when I was first talking about these sedimentation velocities, like how many meters do we expect it to fall in 1 second? Not many, in fact, a very small portion, right? And so that 10 to the minus fourth, 10 to the minus fifth range feels pretty good about accuracy there. Okay, so that's part of our answer. That part makes sense so far? Okay, so then VS, here's where we use the physics. So that's going to be our acceleration times the difference between the density of particle versus density of water times the diameter of the particle squared divided by 18 times the viscosity. Okay, so then here, really the only remaining tricky part is perhaps the conversion for density of the particle. Okay, so for the particles, let's go ahead and take this particle density and say, I'm just going to outline a little section for us to work with that. This rho p, 2.2 grams per cubic centimeter, we can do the formal derivation, which is always a good idea, but there's also a little bit of a shortcut that I'll explain in a moment. So 2.2, let's go ahead and convert that to kilograms. That would be 0.0022 kilograms per cubic centimeter. And then we can multiply this by the conversion between cubic centimeters and cubic meters. And to do that, I always like to say, so we need cubic meters on the bottom. So how many centimeters in 1 meter? And then what I'm going to do is I'm starting with just the one dimension, let's say that's going to be 100 centimeters per 1 meter. And then I'm going to say, well, we need it cubed. So you have to cube that entire conversion. So it's going to cube the 100 there. And if you didn't do that, that would be going to be off by quite a few decimal places. So that's going to yield, when we do that, 2,200 kilograms per cubic meter. Now, the shortcut to that would be, if this is at all a reasonable, normal scenario, meaning I'm not taking like uranium pellets and calculating their density and stuff that are going to drop real fast. If it's some particle that's, that you would normally treat in a water treatment system, then it turns out that the density is going to be pretty close to water, but a little higher, right? So it's going to be on the same order. It's going to be pretty much on the thousands, because we know that for water near room temperature, near 5 degrees Celsius, it's pretty much 1,000 kilograms per cubic meter. So that's known. We had that in our lookup table. We already know that, and that's in the right unit. So we know that on the one side of this, it's going to be approximately 1,000. It's going to be something minus more or less 1,000. So in order for the particle to settle, it's got to be more than 1,000, and it's likely going to be not too much more than 1,000, maybe twice as much, maybe if we have a really dense thing, 3 times as much, but it's not going to be 10,000, right? So you can actually take kind of a shortcut and say, well, I just know that's going to be in the thousands, so I'm going to move the decimal place until it works, right? I don't recommend, but maybe as a way to check your work, right? So we can continue at, say, 9.81 meters per second squared for the acceleration due to gravity. Then we've got our particle density, 2,200. Good idea to go ahead and write out the units just to make sure you have done the conversion, because you'll notice here if you had not, minus 999.1. Let's get rid of that. Kilograms per cubic meter. All that times our diameter, which was 1 times 10 to the minus 5th squared. It's meters. Sorry for the mess here. All of that divided by 18 times our dynamic viscosity. And remember, from the lookup table, included in the units were that 10 to the minus 3. So when we look it up, I think it was 1.139 formally, because I rounded there, times 10 to the minus 3rd, and that's kilograms per meter times second. So you could go through and double check to make sure your units are satisfactory. At the end of the day, you should be left with meters per second, all told. And then it's just a matter of putting that into a calculator or into Excel. Does that make sense in terms of where we're getting each of the numbers? All right. So once we do put it into Excel, we get a value there of 5.75 times 10 to the minus 5th. Meters per second. Okay, and we can then compare that to our design velocity, the V naught, and say, well, that is actually less than V naught, which was 3.8 times 10 to the minus 4. So times 10 to the minus 4 versus times 10 to the minus 5. The minus 5 is clearly smaller, and so that tells us that, nope, the answer is no, not all will settle. Okay. All right, does that feel better now in terms of how to approach the problem? Okay, it is, once you know what to think about each piece of information, it becomes more straightforward. But the first time you look at it, definitely potential to throw you off, and that's why I forced you to take a look at it and encounter those issues, like, oh wait, what diameter are we talking about? Like, what's the volume? all those pieces to sort of get you in the habit of practicing building these problems up. Okay, so just a quick recap of last time then. We were talking about the critical settling velocity. Already covered just about all of this. That's V naught. And then for some random other speed, it may or may not make it through. And I wanted to just give you a couple slides where it's all written nicely on, well, what happens in those cases for the particle removal. Kind of already talked about this aspect, but doesn't really matter the shape of your reactor. You're still going to have an area of the basin that's going to be critical for the Q over AB. And so when you're doing a sedimentation problem, you may as well just go ahead and solve for the area of that basin or write it down somewhere because you're probably going to need it. Okay, I think that's all I was going to say with that one. There's one kind of a neat alternate type if we want to go fancy, and that is to use what's called a high rate settler. And essentially it's just adding shelves. Because if you think about it, that the fact that the area of the basin is really the controlling factor, you can kind of multiply the area just by adding more shelves for the particles to settle on. And so they're not always practical because they're going to require a little bit more care for the mechanical maintenance, the cleaning, the potential for accidental kicking the sediment back up into solution. So there's some potential complications, but for some cases, it makes a lot of sense. You can actually get either a higher flow rate or slower particles to settle just by simply adding these shelves. Because it's just, in essence, it's less distance for them to drop, which makes sense. But the way mathematically we can look at it is we just, in this case, quadrupled the surface area of the ground in which we're settling them onto. So that's a pretty neat system for cases when it's applicable. There's another interesting treatment design here. It's called the upflow design. Probably won't really do too much with this, but essentially you have water flowing upwards and then it's harvested over the edges of a system like this. And it's probably circular. It's definitely this trapezoidal sort of shape so I guess that would be conical. It does that so that as your water nears the top, it slows down. So your velocity here at the top is slower than what's coming in at the bottom. And what this does is that means the speed at which the particles have to fall has to at least exceed the speed at which water is going upwards, right? Which is kind of a silly design in some sense. Again, there's probably a few niche circumstances where this makes a lot of sense. Probably not drinking water treatment for the most part, because the all or nothing gamble is not quite as good, I would imagine. So in this case, we can say that is the V naught as the speed at which water is flowing upwards right at that moment. And so then the Vs has to oppose that in order to stay in the chamber, and then presumably eventually it'll collide with some other stuff and sink faster and be removed. So that's kind of an interesting one. That's if it's V naught is greater than Vs, you just don't get any removal. So just wanted to kind of highlight that as an interesting little anecdote there. And then I wanted to give you this a little bit more clearly. I know we talked about this last time, but for the case when we want to know what portion of particles are removed, we can think about it in terms of the geometry. So instead of having a line that goes straight from the highest point down to that spot where we say, okay, if it's not removed by here, then it's not removed at all. Instead of having that, which would be the V naught, we're going to say, well, what happens when we have a particle that's settling slower? Well, if we have water filled with that type of particle, and this has some Vs, well, it turns out that some of them are going to enter the chamber at a lower position than the very highest part, right? Because there's actually particles all throughout. So they're all going to be doing this trajectory wherever they happen to be. And so we're going to get some portion of particles settled if there is, if we have a proper slope. It's just not going to be all of them. So in this case, we can take a look and figure out exactly how many simply on the basis of that geometric comparison. And like we said last time, we can look at this in terms of, I guess it's probably called a parallelogram or whatever. We have A and B, and those sections are going to be the same on that side, given the straight lines and the right angles and all that. That means that the distance is going to be essentially directly proportional to the velocity. So we can just look at the velocity change and say Vs over V naught is our proportion, and we can turn that into a percent. Because if the line that gets us to the very bottom, if that's V naught, that's, let's say, 100%, then we take some portion of that, we give it the same amount of time. That's just a difference in distance that it fell. So it's directly proportional. No other factors taking an impact. So that's where we get that. That's pretty handy. So then we can use that. If we were to take a look back at our problem a minute ago, we could also calculate what portion of those particles were actually removed, right? So it was something like, V naught, I think, was 3.8-ish times 10 to the minus 4. And Vs was, 4.75 or something, times 10 to the minus 5th. So we could do this divided by 3.8 times 10 to the minus 4th. And that should give us some ratio. And if we look at it, that's like 0.4 divided by 3. I'm going to round and make it easier. I'll say it's 0.4 divided by 4. And so that's like 1%, or did I 10%? It's about 10%, right? So something like 10% of particles removed, because the speed of one was about a tenth of the other. Okay, so that's just sort of an example, thinking back onto the one we were just doing a minute ago. Does that make sense? All right. And we could also use this, if we could even design a system to say, well, we need at least 75% of these particular particles to be removed, and that's my design criteria. So then we could work backwards, right? We could say, oh, well, we have this Vs, these particular types of particles, but we only need to remove 75% of them. So I'm going to apply this and make some ratio between Vs and V naught, 75%, and design my system that way. So just a few things we can do with that. All right, so that is essentially primary sedimentation that we've discussed and covered. We're going to come back to sedimentation in a sense, meaning that the next step is to do coagulation and then flocculation. And then we would sediment again with whatever new particles we have that are presumably larger and easier to settle. But the same math is going to apply because we're going to make these same assumptions. So we're not going to do more lectures on sedimentation per se, but it's going to be a part of other aspects in the course, right? It's also going to be used in wastewater. So this topic will definitely be around for the semester. So then coagulation. What we want to do with coagulation is cause particles to stick together. So we're going to go through a little bit of the terminology and why it works today. And then towards the end of class and mostly next time, we'll talk about, okay, well, how do we mathematically model how quickly it happens so that we can design some sort of a system on that basis. Okay, so first of all, what are we trying to remove? In the last problem, we were talking about 0.01 millimeters. That would be the same as 10 micrometers. So if 1,000 micrometers is 1 millimeter, then 0.01, that's what we had in problem 6.1. Okay, 10 millimeter, or excuse me, 0.01 millimeter silt particles, 10 micrometer silt particles. Just kind of as a reference here, that's probably the very smallest thing that we could imagine seeing with our naked human eye, right? That's at the very edge of visible for us. That is, maybe there are human hairs that get a little bit smaller, but if you can think of the smallest human hair you've ever seen, that would be the diameter of the particles we were just talking about. Pollens are often around that size, sometimes larger. Algae, there's many algae cells that are smaller, but some that grow bigger. Bacteria are all pretty much smaller than that. Maybe the largest ones get about that. And in fact, I think there's a couple species that reach 50 millimeters, or excuse me, not millimeters, 0.05 millimeters, so 50 micrometers, which you could actually see with your eye, which is kind of crazy to think about. So there are a very, very few weird bacteria that you could potentially see without a microscope. I think it's very much the exception. Most bacteria, and certainly the ones we care about for filtration treatment, are going to be smaller than that. So I'm going through these steps because it's kind of interesting to think about. We had this system, and can it remove these clay particles, essentially? That's the silt. The answer was no. And then if we think about it with respect to all these things, a lot of these we would want to remove also, and they have no chance, right? So that system would definitely not remove any bacteria by sedimentation. Maybe some algae, definitely not these Cryptosporidium or Giardia cysts, and certainly no viruses, right? They're way smaller. And even if we didn't care about the silt, we certainly would care about these things. Of course, I think we would care about the silt if for no other reason than to not clog our pipes. Okay, so particle stability. This is the technical term for why particles will hang out in solution and stay suspended. So if you have a bottle of water and it's kind of murky, you can even think of milk. It's got a lot of suspended matter. If you've ever curdled milk, you can see it all start congealing. It's kind of a little bit of a coagulation process. And then if you were to let that curdled milk, let all the stuff settle out, or you filter it, you'll actually get a fairly clear liquid. It's still maybe a slightly yellowish or off-white color, but a lot of the particulate matter has been removed. So if you think about tea versus coffee, coffee actually has a lot of colloids. It's hard to see through it. But tea, usually you can see through it because it's just stained. Or like muddy water, if you've ever looked at a muddy river or something, there's a clear difference between the mud that's suspended, particles everywhere scattering the light, you can't see through it, giving it a brown color, versus a clear but stained water that would be like sort of a brown or other tint, but you can see through it still. So that's kind of what we're talking about is the particle stability, meaning particles are hanging out there, and if you were to try to look through it, the light's getting scattered in any which direction, so it looks murky. And particle stability then is what we call it when they are freely floating and not sticking together. So the destabilization is what we're after if we're trying to get them to stick together. So, all right, so particle stability, this is stable, we'll say stable against sticking together. Sticking together and dropping out. Of the solution. Okay. So essentially, we have a force balance that's going to dictate whether or not the particles are stable. And usually, particle charge, so surface charge of said particles, is going to be the primary way that they can be stable against sticking to each other. The reason for this is usually on some surface, we end up with a net negative surface charge. That is very common for most materials in water, is that they'll often have kind of a negative surface charge. There's a couple reasons for that. I'm not going to go too far into it, but there's a little bit of organic chemistry in terms of you have some molecules and some part of the stuff, and then maybe some acid-base chemistry where you can have an OH minus or maybe that was an OH and then the H leaves and then you're left with O minus, something like that. A lot of times there's a bit of acid-base chemistry that leaves you with some net negative charges. Or in the case of clay particles, like in other minerals, sometimes you get occasional substitutions where it was some mineral of aluminum and iron and something else, and then it swaps an iron for some other metal, and that gives it a negative charge. Can also happen for positive charge, but the typical is you end up, most suspended particles are going to be negatively charged. So most surface. So that's pretty common to have some negative charge. And essentially that's like a force field, because if both particles have a negative charge, they are repelling each other based on that electric field. So that would be a kind of electrostatic repulsion. And it actually is slightly more elaborate than that. I'll draw and talk about that in a moment. But essentially what's happening is they're giving each other the stiff arm, and until you get them close enough, they're never going to stick together and drop out. So our coagulation process then is almost like we're trying to be nefarious and get all the bad particles to hang out together and drop out of the school, right? We want them all to cling together and drop out of solution, right? That's the destabilization. Destabilized their little environment. So the attractive forces are called, it's actually quite a few different forces at play. There's like kind of the electron shell, so atomic forces, magnetic forces, all these really, really short range forces that will pull them together. If you've ever seen a gecko or a frog climbing like on a clean glass window or something, they're actually using van der Waals forces. They're allowing their little sticky pads to get close enough where there's none of these repulsion forces, and it's just they're so close together that these the little electron clouds and stuff are pulling strong enough to hold them there. So that's actually van der Waals attraction forces. They're actually very strong. So we'll say for the electrostatic, these guys typically fall off, like the strength diminishes on the order of something like, I think it's 1 over radius squared. So radius meaning distance from the particle. So that's like, it diminishes as you go out into solution, but it's a lot different than the van der Waals, which diminishes, I think it's radius to the 4th in a lot of cases, maybe even to the 6th for some of them. So you can see then there's a big difference between, the distance away from the particle is going to matter a lot. It's a little bit like playing with magnets. When you pull them close together, if you've got them repelling each other, then the closer you get, the harder it is to push. Or if you flip it, they're attractive, they're not going to be very attractive until you get very close, and then they're really stuck once they stick, right? So that the closer they are, the stronger that force is getting. That is true here on a kind of 1 over radius or distance to the 4th. Okay, so essentially what we want to do with coagulation is overcome this electrostatic repulsion in some way to allow the van der Waals to take over, for them to stick together and make larger particles that will be more likely to fall out of solution. So what actually happens in a real system with charged particles like this is we have ions in solution. We've got, if nothing else, we have the acid-base chemistry of water. We have H plus and OH minus, right? So in any solution of water, we're going to have some ions. Usually we'll have more than that. A lot of times we'll have some sodium, some chloride, and a whole host of other ions, right? Especially if we're talking about a natural water. So these ions then are going to also be attracted. So we'll have a layer of positively charged ions that comes into contact or close by to satisfy that charge there. And then essentially this will happen again. These are going to be diffusing a little bit, but attracted pretty well to that surface charge. And then we'll get a second layer that is more loosely associated, a little more diffusion, a little less well ordered, with little negative ions, occasional positive hanging out, just diffusing around. And so what ends up happening is we get what's called a double layer. So electrical double layer, essentially what this does is extend that electric field out a little bit further, right? So this is almost like a little barrier that's part of the reason where we have that that extension out into solution. And as we'll see in a couple minutes, just for reference, the distance of this electrical double layer is often something like tens of nanometers. One of these particles, of course, depending on the size, let's say a virus particle would be something like 50 nanometers. So if you imagine a 50 nanometer sphere, and then it can't even get closer than 40 nanometers away, because this is going to be on both sides, right? This is going to be a double layer here and a double layer here, doing the whole stiff arm thing to other virus particles, which is why virus particles can stay stable and not all clumped together, and they're just one useless thing that can never transmit anywhere. They want to be dispersed and be able to spread themselves wherever and infect as many host cells as they can. So particle stability here, that's what we need to overcome, is this whole electrostatic barrier system. So here it is again, a little bit better drawn, but this whole system here where a particle, and essentially this is going to have the surface, it's not showing it, but it's going to have negative charges here. And so those are positive ions that are coming to counteract that or to attract it by it. So then this system of the two layers of ions is kind of what we call that electrical double layer. That's different from what happens out in solution. So the bulk liquid here, that's just the generic amount of ions floating around in the solution. Okay. There is one key component here. If we make a very, very, very clean water, there's going to be very few ions. And what that's going to do is that's going to drag, by osmotic pressure, drag these ions further away from the surface, because there's the osmotic pressure trying to make all of the ions in solution distributed pretty evenly. So that's if we had a very dilute case, let's say dilute, these guys might be near the surface, but not at the surface, or at least they're more spread out. And then the next layer would be out a little further. I would just be expanding that whole system. Whereas if you had like super salty, it would just be, they're really up close, bunched up real tight, because they might as well be, right? There's some function, this gradient aspect of solutes in solution. And so since there's so many so tightly packed anyway, they're just going to bunch up real close. So the salinity then, or the ionic strength, which we'll talk about in a couple of minutes, is really important. The other important aspect is if you have a surface, you can, when we think of how to create that salty environment, let me back up a step. So in the case of the salty environment here, the electrical double layer is much shorter than this one, right? It's a lot less distance into solution for the salty case. So we've compressed that double layer. That makes it more likely that we can get the particles to actually stick together. So we kind of want we want a condition like this, even though we don't want to create salt water, right? So as we're thinking about that, one thing we can do is use a charge that is not just +1. So if we use sodium, that's just +1, whereas we could do, let's say, calcium, which is +2, or even better, aluminum, which is +3. And if we do that, if we think back on this case, if we can satisfy 3 of these charges with a third of the space, it really starts condensing things quite a bit. So rather than having 3 different atoms or ions floating around, hovering in this area that are each about the same size, if you can take one that's also about that same size and compress it and satisfy so much more charge, it's really going to diminish this double layer a lot more so than just the +1s. So we have a couple graphs showing that, and it's kind of showing how much of an impact we have. And so this first big one in the center here, this is looking at turbidity. That's a measure of how many particles are in water. When I was talking about it earlier, that's the murkiness of muddy water. Right? Scattering of light is how we measure it. I can even make my water bottle turbid with air bubbles just by shaking it. Of course, the turbidity goes away really quickly, so right now you can't see through it, but as soon as I stop, turbidity is basically gone. Sometimes you'll even get water from a water fountain and it looks like it's milk. Sometimes that happens. I don't know what's up with the water fountain, but essentially if you let it sit there, they're actually really tiny air bubbles. And so they will reverse sediment actually out. And once they've done so, it's pretty much clear water after that. So essentially that turbidity is what we're looking at here on this graph. We start with some dirty water. So the turbidity is at 100%, and we're adding salt. If we're adding an aluminum version of salt, that's when it drops. So this is a turbidity on the y-axis and then the dose of the coagulant, so how much mass we're adding. And let's start with the sodium. So we go all the way out here until right there. Once we've added 10,000 milligrams per liter or 10 grams per liter, then we start getting some impact. Then it's by the time we've added 10,000, we've basically sedimented everything. So that's 10 grams per liter. And as a reference, seawater is typically about 25 to 30. Lake Pontchartrain is about 5 grams per liter, depending on where you are. So we'll just say seawater is somewhere around 25. So we're nearing the point where we're at seawater, right? We're getting on the scale of seawater before we're getting this coagulation effect based on just adding a sodium type salt. There's also going to be the Cl minus or something like that associated, but the cation, the positive charge, is really the first thing that matters, and it's more common to be able to adjust that. So we sort of describe these as just the cations. Okay, if we do that with calcium, we see that we need quite a bit less. So 100 times less, that would be about 100 milligrams per liter before we get the impact. So much better, and it's not just twice, right? It's a much bigger factor because that compression is so effective. If we go to aluminum, we're all the way down to about 10 milligrams per liter required. And that's really good news, especially because sodium is notoriously difficult to get out of water. We could do desalination, we could do evaporation or something, but that's a lot of energy. So if we can add something that can easily be taken out, that's better. And it turns out aluminum is very easy to then reprecipitate as aluminum hydroxides just with some pH manipulation. So, and in fact, we even use that for the coagulation. We cause it to precipitate. That's causing solids to grow. That helps captures more particles. So turns out that aluminum, and in fact aluminum sulfate is what we call it, it's alum, is a really good thing to use for all those reasons. Just real quick, if we take a look at how far out into solution our charge, our little barrier, electrostatic barrier here, these small graphs here, these are potential in millivolts. So this is essentially our electric field. So field strength, I guess. And then it's by distance in nanometers to give us some indication of kind of how far are these extending. So if we, and then we have three different lines. This is three different concentrations of sodium chloride at the top. So NaCl, if we do 60 milligrams per liter. And let's just imagine for a moment that a field strength of 20 millivolts, whatever that practically means, let's just assume for a moment that's the amount of force that's required to keep them separate. Okay, so if we take a look at it that way, then we see this is extending out to about 20 nanometers for the 60 milligrams per liter. If we then take a look at 600 milligrams per liter, that's a little under 10 nanometers, so maybe 8 nanometers into the solution. And actually, we have a nice figure here saying that, okay, once we get up to 600, we're right about here. That correlated to, I say, about 8 nanometers. That's not enough. And so it turns out that once we add 6,000 milligrams per liter, we're getting to right here. And that's just a little bit under 5 nanometers. And so that would correspond to right around here somewhere. Then we're getting under 5 nanometers as our barrier. And so that seems to have shrunk enough to say, all right, these other forces are starting to take dominance, and then our van der Waals can take over and cause them to stick together. So it turns out something like 5-ish nanometers is what we have to achieve in order to destabilize the particles, if that's the correct potential. So guessing a little bit here, but something like that would hold true. You could also look at the same type of plot, but keep the concentration the same and just change the charge number. That's the Z. It's a +1 charge versus a +2 charge and versus a +3 charge. And then you could look at, okay, well, again, assuming we have some critical potential here, we could look at how much of a difference changing that happens, right? So the +1 has 25 nanometers, the +2 has 15 nanometers, and the +3 has about 9 nanometers for that particular example, right? So whatever dose they used in that case. So just a way to visualize and think about how important that aspect of satisfying these charges becomes when you can satisfy all of that in a smaller space. Okay, does that make some sense? All right, so there's one chemistry term I want to talk about, a way to quantify ionic strength. That's the term. Essentially is the strength or the amount of ionic species in solution on a molar basis. So it's a pretty simple term, so I didn't bother including it in the chemistry refresher. We'll really probably only use it for the coagulation stuff, but I figured I'd walk you through it, and it would also be a good example, a good moment to practice some of the fundamentals for chemistry. So our definition for ionic strength is I, which is ionic strength, equals 1/2 times the sum of all the ionic concentrations times their respective charges, which is Z, squared. So it would look something like I equals 1/2, if we just have A and B, let's say, times the molar concentration of A times the charge of A, we'll say Z, give it ZA squared. So that means even if it's a negative charge, it's going to come out as positive, which is convenient, plus B, molar concentration of B, times B's charge squared. So that's if we have a system with just A and B. So that could be sodium chloride, or it could be magnesium chloride, for example. So I'm going to go ahead and walk you through this problem as an example, and then give you a second problem that's slightly more complicated to practice. Okay, so and again, the concept here is that if we increase the ionic strength, we're going to decrease the electrical double layer for all the reasons we just talked about. Okay, so we have 100 milligrams per liter of magnesium chloride here. And the problem prompt here is to find the molar concentration of magnesium, of chloride, and then the ionic strength. So first of all, I'm going to go ahead and say, well, we need some information about magnesium and chloride. That way we can get the molecular weight. So magnesium, did this earlier today, so 24.3 grams per mole, if you were to look that up in a periodic table. And chloride is 35.5 grams per mole. So that means if we take 2 chlorides and the magnesium, it's 90 something. 95.3 grams per mole. Okay, so then the process I would take, say we have 100 milligrams of this stuff, and we know, I even gave you the sort of the reaction here, or the stoichiometry. We have 1 mole of magnesium chloride forms 1 mole of magnesium, 2+, and 2 moles of Cl-. So we have a molar ratio here that we can use to find the molar concentrations. But first we need to know essentially how many moles per liter of the magnesium chloride molecule did we add in the first place, because that's what we were given. We're given the 100 milligrams per liter of MgCl2. So that's going to dissolve. So we need 100 milligrams. I'm going to go ahead and rewrite that as 0.1 grams per liter of MgCl2. That's just converting from milligrams to grams. And I'm going to say we're going to multiply that. We could divide it by the molecular weight, or you could just do multiplied by 1 mole, just doing the inverse essentially, per 95.3 grams. And again, you could write all this out, MgCl2, to avoid any confusion. And when you multiply this, then you'll be left with a molar unit that's moles per liter of this stuff. So that's going to give us 0.1 essentially divided by 95.3. That should give us a value of 0.001 with some decimal places. So we'll just say 1.05 times 10 to the minus 3 moles MgCl2 per liter. Okay. From here, we can say, well, there's 1 mole of MgCl2 per 1 mole of Mg2+. So the molar concentration of Mg2+ should be equal to exactly what we just calculated. 1.05 times 10 to the minus 3rd moles per liter, which you can also write as capital M. So far, so good. So then our chloride concentration, Cl-, is going to be equal to 2 times that, because we had 2 chlorides for every 1 mole of that dissolved. So really, that's just going to be 2.1 times 10 to the minus 3rd. I'm being a little bit lazy here with the decimal places. If we were to carry them properly, as Excel I'm sure does, turns out that would be 2.098. So yeah, that would turn out to be 2.1. But just noting that there's some rounding there that could take an impact. I like to keep all of my rounding in place while I'm doing the calculation. So do not round and then round for the final. Right? That's the technically better way to do it. Okay. Anyhow, so that's our magnesium, that's our chloride. So that gives us a way to find our ionic strength, which is then 1/2 times this 1.05 times 10 to the minus third times essentially 2 squared plus 2.1 times 10 to the minus third times 1, so I'm just going to leave it like that. I guess for the sake of clarity, maybe I'll go ahead and write it. Okay. So then our ionic strength then is equal to 0.00314. And technically, that's kind of a molar unit. It's moles of charge per liter. So we can leave it moles per liter is fine. All right. How's that? Does that make sense? Okay. So for a second example, instead of using 100 milligrams per liter of just magnesium chloride, what happens if we use 50 milligrams per liter of magnesium chloride plus 50 milligrams per liter of NaCl? Okay, so I'm going to let you take a minute or probably 10 minutes to try that. I will write up the stuff you need from the periodic table here. So mg atomic weight was 24.3 grams per mole. Cl 35.5. Sodium, I think, is 22. Or was it 23? I'll look that up real quick. And then the ionic strength equation, remember, is 1/2 times the sum of the concentrations times their respective charges squared. Okay, and I'll get you the sodium thing in just a sec. Yeah, 23. Probably. Yeah, I would think so. Thank you. All right, so I'm going to walk you through the process. I don't think I'll have time to do all the numeric calculations, but there's one tricky part where I was hoping for you to recognize, or I'm hoping that by me explaining, you can recognize something that you want to make sure to have correct in terms of your analysis of a chemical system. So first of all, what I'll start with actually is saying at the end of the day, what we want is a ionic strength equation that looks like this, right? 1/2 times, we'll go ahead and say Na plus the molar concentration, so we're in brackets, that would be times 1 squared plus Cl minus in brackets times -1 squared plus the Mg 2 plus times 2 squared. Now, the reason I'm writing this out is because I've seen some students say, oh, look, we have chloride from here and chloride from here. They're both dissolving They're both adding chloride to solution, but that doesn't mean we have two different concentrations of chloride. We have one concentration of chloride. Two different sources, we just have chloride in solution. So we're not going to do anything weird or special with different sources of this. We are just calculating the concentration of chloride in solution. Right? So there should just be one chloride here. And to do that, just like we were saying before, we can get this into moles per liter of NaCl. And since it's a 1-to-1 ratio there, that's going to be the same thing as the Na plus and the Cl minus contributed by that. And so then for this guy, we'll have the same deal. We're going to give that moles per liter of MgCl2. That's going to give us moles per liter of Cl minus contributed from there. And I know I'm writing them separate here. So just bear with me for one moment. And then, excuse me, that'd be two of those, two chlorides. I'm just going to write it as chlorides without the concentration. I'm confusing you with just the concentration brackets here, right? So, and 2Cl minus per. And so then when we calculate the total, so Cl minus concentration, this would be equal to this guy plus the amount we find here, right? So it'd be that amount plus that amount for our calculation. Does that make sense? So we have some number of moles per liter added from one source. We're just going to add that to the next source. We could have 5 different sources of chloride. They would all come together to make one concentration, right? Sodium would be very simple. That would be just the amount added here. And then likewise, magnesium, we just had one source. So then we'd put all those into the correct places. Did that make sense? Okay. Yeah. So and maybe it won't make a difference sometimes, but it's best to just think about it as that is the concentration in solution. Right? We've added it into various forms, and there we go. Okay, so we'll pick up here and talk about flocculation next time. Yeah. Have a good weekend.